Welcome to this important topic of internal stability. I will show that if there is unstable pole zero cancellation, there will be instability demonstrated through an example. Let us start with the standard closed loop system. The notion in undergraduate classes is that the output has to be stable, but we will show that the output being stable alone is not sufficient. Every signal in this loop should be bounded. If any signal is unbounded, this will result in saturation, overflow or explosion of the physical property indicated by that variable. If every signal is bounded, we call the system to be internally stable, or the transfer function between any 2 points to be stable. We will show that if the output is stable and if there is no unstable pole zero cancellation, we will have internal stability. We want to show that the transfer function between any 2 points to be stable. In the system that we considered earlier, let us introduce an auxiliary input R2. So this is the reference signal we had. We introduced this new signal R2. What we can show is that if the transfer function between two specific outputs E1 and E2 and the two inputs R1 and R2 are stable, then every variable in the loop will be stable. So that is easy to see. I am going to ask the listener to go through that and verify it. Let us write the transfer function between E1 and R1 that can be obtained as 1 over 1 plus GC. So between E1 and R1 it is easy to verify. For this calculation you may make R2 0 and get the transfer function between R1 and E1. Similarly, the transfer function between E1 and R2 is here, minus G over 1 plus G GC. For this one can make this R1 0 and get the transfer function between R2 and E1. Because of the minus sign here, you get a minus sign here. It is easy to arrive at the next line. You can verify this. As mentioned earlier, the other loop variables need not be considered if R1 and R2 are bounded. As a matter of fact, this is the only other variable that is not considered, but if we say that E2 is bounded, R2 is bounded, then naturally this variable also has to be bounded. Alright, we start with the same transfer function and I am going to substitute for G and GC from here. Let us take the 1 1 term and expand it. So what I have done is I have substituted for G and GC from here, simplified to arrive at this transfer function. Similarly, one can substitute and simplify for other 3 terms to arrive at these. So here is the transfer function matrix for E1 E2 in terms of R1 and R2. Now suppose D1 and N2 have a common factor. Suppose G is unstable. So it has a pole outside the unit circle. Supposing I just want to cancel this by this N2, place a 0 exactly at that point and cancel these two, for example. So this Z plus A is that factor which has a 0 outside the unit circle. Okay, I am calling it as unstable Z plus A. What we will show is that even if I take this to be stable, the second term will become unstable, making the transfer function between E1 and R2 to be unstable and hence violating internal stability. We will do this in the next slide. So this is G and this is GC. Remember, the unstable pole of G is cancelled by a 0 of GC exactly at that location, and A is outside the unit circle. Now, as I mentioned earlier, we will assume the stability of 1 over 1 plus GC. When I substitute these two, will result in this expression. So this says that d1 prime d2 plus n1 n2 prime has its zeros inside the unit circle. That is, this transfer function has its poles inside the unit circle. But the transfer function between R2 and E1, which is the same as the expression I had as read in the previous slide, can be shown to be unstable. Let us construct that transfer function. So that is minus G over 1 plus G GC. Let us substitute these two and simplify, and I will get this. Note that after all cancellations I still have Z plus A, and hence this transfer function is unstable, and hence a bounded signal injected in R2 will produce an unbounded signal at E1 or the system output Y. So what we have shown is, if you try to cancel an unstable pole with a 0 at the same location, at least one of the transfer functions will become unstable. Internal stability is the same as all variables in the loop to be bounded for bounded external inputs at all locations. It can be checked by the closed loop diagram as we did earlier. The converse also is true, namely the output is stable and there is no pole 0 cancellation, then we can show that the system is indeed internally stable. I am not showing that here, but it is explained through a problem in the textbook. I encourage you to try the problems at the end of the chapter in the book. With this, we have completed the important topic of internal stability. Thanks for joining. Goodbye.